My name is Sylvia Howland, and I will be walking you through multiple rounds of deep dives, starting off from our hardware and system level. I'm going to give you basically a bottom-up view of how the system works, expanding on some of the content that Natalia provided in the introduction. Then we're going to flip that around, descend in levels of abstraction to talk about how users interface with the system through our APIs and our process. And then I'll guide you through things like using those APIs, doing some model porting, all that kind of good stuff at the user level. So cool. Hardware and systems. Natalia already provided a little intro to the wafer scale engine 2, the WSE2, both it and now our WSE3, still the largest chips ever made, really pushing Moore's law to its absolute limit. Because we have a full silicon wafer scale chip, we can cram 2.6 trillion transistors onto it, which is very exciting because it means we can in turn fit 850,000 specialized cores, specifically for sparse linear algebra onto it. And because we're operating on a single chip scale, we keep all of our memory, all of our compute on the same chip. We get some truly bonkers numbers for bandwidth. Specifically, you might notice 20 petabytes per second of memory bandwidth and 220 petabytes per second of fabric bandwidth. We're really proud of this. It's able to give us cluster scale performance on a single chip. So in terms of how this is actually working under the hood, right? We talk about 850,000 cores. We call those individual logic units processing elements that are basically going to be presented logically as a 2D array, each of which is going to have access to about 48 kilobytes of memory, all of which is exactly one cycle to perform read or write on the local memory, and in addition, one cycle read or write to perform memory communication to every processing element adjacent to it in the grid. Have 16 and 32-bit native floating point and integer data typing. And basically the way the hardware is going to be working at the lowest level of abstraction is we're going to program all of these processing elements to do computation and communication in a data flow. Obviously, we're going to end up abstracting this so that you as a user don't have to worry about it, but we're going to have a bunch of nice implications and side effects arise as a result of this architecture, so it's useful to review. Essentially, we have a flexible communication structure. We're going to have programmable routing between these processing elements. We can have either static or dynamic communication routing, which internally we refer to as colors. And in our SDK, that'll be covered on day 2. I'm very excited to hear about our SDK at all times. It's very cool to see people interfacing with this. In addition to those colors, those different data routes, we also have the individual data packets called wavelets that are getting handed off, passed between these processing elements. Key reminder, only one cycle to do that transfer. So we can propagate and perform computation on this compute fabric very, very quickly. Collectively, across all these processing elements, again, 40 gigabytes of on-chip SRAM, including data and instruction memory, one cycle read-write. We can operate very, very quickly if we can synchronize across all these processing elements effectively. So on top of that chip, on top of these CS2s, we have a number of other components that Natalia mentioned a little bit of that go into building our wafer scale cluster. Because really we want to go from having this really cool chip to having a high performance, really scalable machine learning, high performance compute appliance. Sort of all in one solution. It's going to be scaling from one to many CS2s, and it's going to be flexible in a number of different ways. I'll be getting to here in a bit. Essentially, very nice. We can scale the CS2s independently as sort of our compute element from our parameter storage. Don't worry about that too much right now. We'll get into a lot more detail on that very soon. But the sort of takeaway, the big benefits of this, we can run enormous models on a single CS2. We can scale up the number of CS2s if we need to perform more or faster training. But we can scale very, very large on a single machine. We'll also be able to scale up model size with just basically a single line code change or just changing a few config fields, essentially. We'll be able to scale out really well extremely efficiently with near linear performance as we expand our compute. And like Natalia said, one thing that's really nice as an end user, you can always treat this appliance as a single logical device, no matter how much is going on under the hood, no matter how many CS2s or system memory you're adding in, always viewed the exact same way from a developer researcher perspective, which is quite nice for a small team. And then another thing that I'm really excited about, as someone who comes from a small research team, national lab type of background, this entire appliance is going to scale based on simple data parallelism. You don't have to worry about the super complex model or tensor parallel pipelining distribution that frequently introduces a ton of code overhead and tends to turn machine learning and scientific problems into engineering and HPC problems, which can really slow down iteration and time to innovation. Excellent. So I mentioned before that we can scale different aspects of this appliance independently of one another. In the middle of this, we can see we have our CS2, our basically compute cluster. The exact number of CS2s there isn't important because what's bottlenecking our model size is really what's on the left here, which is our external model memory, essentially a central parameter server, where if we just add more memory storage and then a little bit of CPU compute, that's what's determining the maximum size of the models we can operate on. And then we're going to get into how this is implemented a bit later. But we stream those model weights to our CS2s one layer at a time. And then we're also going to have some external training data storage that's going to be feeding in our data samples and our labels that the CS2s can use to compute those gradients, stream them back to the central parameter server to get our model updated. What's nice about this, right, is we've really sort of purpose-built a holistic solution that is able to exploit the fact that neural networks use different types of memory and compute for different elements of the machine learning problem, right? Historically, if we're coding on GPUs, we have this really tightly interconnected problem of compute, memory, communication, and how we scale all of those up at the same time to become incredibly messy very quickly. But in this case, right, if we just want to handle larger models, but we don't want to, or we don't necessarily need more compute, that's okay. We can just make our parameter server larger and not touch the CS2s. If we want to run a whole bunch of experiments extremely rapidly on smaller models, that's okay. We can use a smaller parameter server with lots of CS2s. We can really sort of target what we need for our solution and not touch the other elements necessarily. We end up with this really elegant abstraction. Lets us scale these elements independently. So we mentioned before, I just casually threw out that we stream the weights to the CS2s one layer at a time. That's because we designed something called the weight streaming execution model, which is exclusive to our hardware and I think is very exciting. So we built this execution model to handle extreme scale neural networks. Basically, like I mentioned, we're storing all of our weights in a central server off wafer. We're going to stream those on to compute a single layer into our CS2s. And then what happens is we're not actually storing the weights on wafer even temporarily. As we propagate through all of those processing elements, those 850,000 cores we mentioned, we're basically discarding the weights and only storing the activations for each layer, because that is ultimately all we need to compute the gradients and update our model in the backward pass. And because of this, we can execute one layer at a time, only store the activations we need. And then once we get labels for the backward pass from our data server, then we can basically go in reverse, pull in the activations and the labels, generate gradients. And then we just we chain rule back down the same order the layers that initially came up on, and we end up with our gradients, which we can stream back to our parameter server and apply. This is nice. The CS2 doesn't need to have that much memory on it. Again, we're only storing basically weights for memory one layer at a time, only saving the activations and the previous set of gradients. We can basically ditch all of those elements as they're consumed. We don't need to have a lot of sort of redundant memory usage going around. And then at the same time, again, for the memory X, we can have a lot of memory, but we only need enough compute to efficiently do our optimizer updates, which is going to be a much lighter set of compute than what we need for all the actual sort of hardcore machine learning number crunching that's happening on the CS2s. And so again, very nice, decoupled, highly efficient process. Something we don't have a whole bunch of breakout slides on, but I think is important to touch on is that I mentioned that we only sort of preserve these weights and activations and gradients so long as they're needed. There's an added layer of sophistication we've implemented where we can pipeline and time the streaming of all of these elements so that as, say, we are consuming or computing updates for one layer of the neural network, say in our backward pass, we can already be applying gradients to some of the upper layers of our model as we are continuing to compute sort of lower level layer gradients in the backward pass. So there's very little bottlenecking that happens. This happens at an extremely rapid pace. And historically, right, there's a whole bunch of different ways we need to scale our model. If we're working on a model that is low data, very small, fits on a single device, no problem, we'll just use a single GPU. If we're using a few GPUs, we'll typically use, right, data parallelism, where we're going to have a copy of the model on every device and just basically split a really big batch of data among those devices and then aggregate the results. This is super elegant, works great until your models get really big, because your model size is going to outpace your GPU memory pretty quickly once we start getting to bigger scales. At which point we're going to have to do some sort of model parallelism where we're sharding the model across different devices. We can either have multiple layers pipelined at a time, which is going to introduce a lot of communication overhead. We need to start storing more and more activations on each device to avoid pipelining issues, to avoid starvation among any of the devices. Or we can do tensor model parallelism, where we're actually splitting the layers themselves across multiple devices. This introduces still some communication overhead and gets a really headache-inducing partitioning problem. What's the optimal way to split my layers? How am I pipelining all of this? Again, our complexity of distribution is going to scale pretty horrifically as our model size and our cluster size increases, as opposed to on the CS2, where again, we only ever have to worry about scaling with data parallelism, which is conceptually very elegant, doesn't require a whole lot of added ML engineering to get going effectively. Excellent. So there was another element of the appliance, which I skipped over before. We have our memory X, right, which is acting as our weight parameter server. We have all of our CS2s that are functioning as our compute backbone. We also have this swarm X element, which is basically an interconnect set up in this tree-like topology that's basically going to let us efficiently broadcast all of the memory X weights to the CS2s efficiently. And then it's going to gather those gradients from the CS2s and efficiently reduce them for consumption on the memory X. The swarm X is important because this sort of middle stage is what makes it so the memory X doesn't care how many compute nodes, how many CS2s there are. And each CS2 is only ever seeing the weights that it needs to process and the gradients that it is spitting out. It also does not care at all about the number of other CS2s. And this is what lets us really neatly encapsulate and abstract away all of this complexity from the user, which is very nice. It also means if we want to add in more CS2 units to scale our compute, all we have to do is slot in those extra boxes and add maybe some more nodes to the swarm X to make sure we're continuing to broadcast and reduce as efficiently as possible. But other than that, these are all nicely disentangled from one another. And there's no difference, again, between a single CS2 or, say, 256 CS2s as far as the sort of conceptual and practical flow of this setup. User interface is always going to be the same. Excellent. So to review the sort of high-level differentiators that our hardware clusters provide, we're going to have those 850,000 processing elements operating on this data flow fabric, lots of complex scheduling that's happening at the low level. We're going to have a large amount of on-chip memory that's super close to our compute that lets us read, write, and communicate lightning fast. This is something we're going to touch on more in day 2. But there are some implications of this weight streaming execution model that make us really, really good and really fast accelerating using sparse models, which is a big upside. Don't have time to get into it now, but keep your eye out for that on day 2. And again, having disaggregated and really simplified this compute versus memory problem. Simple programming, simple linear performance scaling. There's also a link here from 2022, our Hot Chips 34 presentation, where one of our co-founders does a whole deep dive into the hardware and the co-design of all the elements of the CS2. I highly recommend checking it out if you have time. Gets into much more detail than we were able to get into here. Excellent. And so like Natalia mentioned, at ALCF today, we currently have a cluster of 2 nodes of CS2s with a memory X that's capable of supporting up to 30 billion parameter models. This is going to be optimized for generative AI LLMs using NLP, as well as multimodal visual question answering type models. And on this cluster, you can use one or both of those systems with data parallel across both as necessary. And if this were to ever expand, again, no need to change your code as a user, no matter sort of what modifications happen to the cluster at ALCF. You shouldn't have to worry too much beyond like software versioning and all that, but the hardware modifications shouldn't affect any code you write.